This is Unit 1, Lesson 2, comparing rates of change in linear and quadratic functions. So our learning goal for this lesson is to identify and compare the characteristics of linear and quadratic functions. So if we are given a table of values, how can we tell if a linear relationship exists? Well, all we need to do is find the first differences, or find the differences. Find the differences. Okay, and what that means, this is really, really simple. So you're just going to draw yourself these little arrows so that you know what you're doing here. So what we are doing is we're just taking the y values and subtracting them to find the first differences. So 3 minus 7, sorry, that's blurry for you. Let me zoom back out. 3 minus 7 equals negative 4. Here we have negative 1 minus 3 equals negative 4. Negative 5, that looks like a 3. Negative 5 minus 1 equals negative 4. And lastly, we have negative 9 minus negative 5, which also equals negative 4. So we can see the first differences for this table of values are all the same. So that's how we know if it's a linear relationship. So same first differences means it's linear. Same first diffs, linear relationship. Okay, so same first differences means it's linear. If we are given a table of values, how can we determine if it's a quadratic relationship? Okay, so that was linear, right? First differences are the same. Quadratic, we're going to do the same thing. We're going to find the differences. So we're going to start 6 minus 3, 11 minus 6, 18 minus 11, and 27 minus 18. And we can just use our calculators to quickly do that. So we get 3, 5, 7, and 9. Okay, those are obviously all not the same number, right? So we know that this can't be linear. So what we actually have to do, these are our first differences. So those were our first. What we actually need to do is find our second differences. Okay, we know it's not linear, so now we're going to move on and find our second differences. So we have 5 minus 3, always second minus the first, third minus the second, fourth minus the third. 7 minus 5, and 9 minus 7. Okay, so now we can see that these are all equal to 2. So now we have that same number. Okay, so this is how we know this is a quadratic relationship, because the second differences are all the same. Okay, so the second differences are constant. So second diffs are the same. And another way to say that is just they're constant. Okay, so we know that that's a quadratic relationship. So if we're given a table of values, fill in the flowchart with the appropriate terms for determining the type of relation. Okay, so this is a nice little flowchart, that's going to tell us basically what kind of relation we're dealing with. So the first thing that we always have to do is find our first differences. Okay, so we're going to find our first differences. If they are constant, then it is a linear relationship. Okay, if they are not constant, we know that it's nonlinear. If it is nonlinear, we have to move on to our next step, which is to calculate the second differences. Okay, so we're going to find our second differences. If our second differences are constant, which just means the same, then we have a quadratic function. If they are not, we're just going to label that as neither or other. For now. Okay, so neither or other. All right, so let's talk about what degree of a function means. So degree of a function is really, really simple. So basically, all it means is for every polynomial with a single variable, the degree is the value of the highest exponent of that variable. So all we have to do is figure out the highest exponent of the variable. So for example, if we have 4x to the power of 3 minus 2x squared plus 7, okay? So we have x to the power of 3, x to the power of 2, and just a constant number. So the highest exponent is 3, so our degree of this polynomial is 3. This next example, we have x, and we have x squared. Well, x squared is higher than x to the power of 1, so the degree is 2. Okay, here we have a squared, a to the power of 5, and a to the power of 1. Obviously, the highest one there is simply 5. So if you know the equation of the function, its degree indicates whether it is linear or quadratic. The degree of a function is the highest power of the independent variable, which we just discussed. So y equals mx plus b. Linear is a linear relation, right? That's what our linear relations will look like. They will have a degree of 1, always. Okay? If we have an equation in the form y equals ax squared plus bx plus c, this is a quadratic relation. They are always going to be of the degree 2. Okay, so definitely make sure you write that down there. Okay, linear relations are to the degree 1. Quadratic relations are to the degree 2. So you might be given, for example, like y equals x squared plus 5x plus 1. And it might say, the question might ask you, is this a linear or a quadratic relation? We know that the degree here is 2, right? Degree 2, because 2 is the highest exponent. So we would know then that that is a quadratic. Okay, just as an example of why you kind of need to know this. Okay. So this note is a lot simpler than the last, and it's also a lot shorter. So the second thing we need to look at is called function notation. So this is an even simpler concept. Basically, f of x is called function notation and represents the value of the dependent variable for a given value of the independent variable x. So what this means is that literally instead of writing y equals something, all we have to do is replace the y with f of x. So you can see that here, right, in this example. We had y equals x squared minus 4x plus 7, and to put it in function notation, everything stayed the same, except instead of writing y, we just wrote f of x. Okay, so it's very, very simple. Literally, f of x is just another name for y. All right? So in this first case, our point is still xy. Okay, but in the second case here, we have x, comma, f of x. So y is just replaced with f of x. So let's look at a couple examples. So this asks us to classify the following relationships as linear, quadratic, or other. So we know our very first step is obviously to find our first differences. So we're going to draw our little arrows. And you don't have to write it all out, like the 8 minus 5. You can just write that equals 3, 11 minus 8, 3, 14 minus 11, 3, 17 minus 14 equals 3, and 20 minus 17 equals 3. So those first differences are the same, which means this is a linear relationship. Okay, second one here, same thing. We're going to start by finding the first differences. 6 minus 2 is 4. 18 minus 6 is 12. 54 minus 18 is 36. 162 minus 54 is 108. And 486 minus 162 is 324. So obviously our first differences in this case they're not the same, right? So we have to move on. We know this is not linear. We move on to figure out if the second differences are constant. I'm just going to change colors. Draw my little arrows. So 12 minus 4 is 8. 36 minus 12 is 24. So I can continue, and just to make sure, but I know 24 and 8 are not the same number. So this obviously is neither. Okay? Or other. Because for it to be quadratic, those second differences have to be the same. Okay, last example here. And this is something that will come back up a couple times throughout the year, or the quad, I guess. Okay, so same thing. 6 minus 3, 3. 12 minus 6, 6. 24 minus 12 is 12. 48 minus 24 is 24. 96 minus 48 is 48. So again, those first differences aren't the same, so I'm going to move on and do my second differences. 6 minus 3 is 3. 12 minus 6 is 6. 24 minus 12 is 12. And 48 minus 24 is 24. So we see something interesting happening here, and we will definitely get to that eventually. But for now, we can see that our first differences are not constant, and our second differences are not constant. So we are simply just going to label this as neither. Not linear, not quadratic. Okay, this next example is asking us to state the degree of each function. So again, remember, the degree is just the highest exponent, right? So this has exponent 2, exponent 1, and exponent 3. So the degree is simply 3. This one here has exponent 1, and that's it. So that's the degree. This last one is a little bit trickier. You have to kind of distribute first. So this is actually f of x is equal to 3x squared plus 3x. So that one is going to be degree 2, because 2 is obviously larger than 1. Okay, last example here. So a word problem for us. So a migrating butterfly travels about 128 kilometers each day. The distance it travels, g of t, in kilometers is a function of time, t, in days. So write an equation in function notation to represent the distance a butterfly travels daily. So the first thing I'm going to do is just write out the information that I was given. So I know that distance is g of t. Okay, and I also know that our number of days equals t, right? That's my variable. And I know that I travel 128 kilometers times, or that's per day, times the number of days we travel, right? Number of days. Okay, so if I were to write this as a function, I'm simply just going to put g of t, so the distance that the butterfly travels in kilometers is equal to 128 kilometers multiplied by t, which is the number of days. Okay, so the next part asks us to state the degree of this function and whether it is linear or quadratic. So the degree of this function is just going to be 1, right? Because we just have t to the power of 1. And this is where that information from above comes in. When it is degree 1, we know that it has to be linear. Remember, degree 2 is quadratic. So now it's asking us to use the function to calculate the distance the butterfly travels in 20 days. Okay, so what this is actually asking is the distance over 20 days equals 128 kilometers times 20 days. Okay, so this is saying distance, the g of 20 means the distance at time 20 is 128 kilometers times 20 days. We just simply type that into our calculators and we get 2,560 kilometers. Okay, last question here. What are the domain and range of this function, assuming that on average, a butterfly lives for 40 days? Okay, so this is a little bit tricky, right? We're kind of applying that domain and range to a word problem. So we have to think about our two variables. So we have time and we have distance. Okay, our time is going to be our independent variable, right? The time doesn't change based on the distance. So that's going to be our independent variable, which is meaning that we are going to be looking at the domain, right? Because our independent variable is usually x, which represents the domain. Obviously, our distance is going to be our dependent variable because our distance depends on the time. Okay, so if our butterfly usually lives for only about 40 days, we know that that's the maximum amount it's going to live, right? So we know that's going to be our largest value, okay? Obviously, if we're thinking about time, its life has to start at 0, right? So our domain is 0 is less than or greater than t, which is less than or greater than 40. Again, we can read that from the center to make sure it's correct. So t is greater than or equal to 0. Remember, t is days, the life of this butterfly, and t is less than or equal to 40 because it lives about 40 days. Okay, distance on the other hand, okay, so for 40 days, if they can only live 40 days, that means the maximum time they're going to travel is 40 days. So we go back, I'm just going to do it here. We're going to figure out how far a butterfly can fly in 40 days by using our equation that we created. Okay, so 128 times 40, and that will give us 5,120 kilometers. Okay, so obviously, oops, I don't have a whole lot of room here, but I'll just write over. For our range, a butterfly can obviously travel, it can't travel negative, so it's going to start at 0, less than or equal to g of t, because that's what represents our distance, which is less than or equal to the maximum amount they can travel is 5,120 kilometers. So that is our domain and range for this word problem. Again, I will let you know the homework on D2L. This is the end of Unit 1, Lesson 2.